Hopefully you'll realize I'm just as nice as Mr. Mackenzie, just not as old as Mr. Mackenzie. But don't tell him I said that. Right, so we're going into organic chemistry now. Most of you have probably had 151 and 152 with Bob Mackenzie, and he's super, super nice. But we're dealing with a much smaller range of elements now compared to what you were looking at in 151 and 152, because we're primarily concerned with carbon, and it's almost as if carbon consumes the periodic table. We do have hydrogen as a major player as well, because of course the 99% of the chemicals we're looking at are what we sometimes term as hydrocarbons, hydrogen and carbon containing compounds. We do have some guest appearances by elements like nitrogen, oxygen, and the halogens, and that is almost it. We occasionally see a metal like maybe sodium or magnesium or iron in the mix as well, but that is very rare in organic chemistry. So it's mostly about the chemistry of carbon, hydrogen, and a few of the other non-metals round about it. So of course we should all remember our subatomic particles from 151, our protons, electrons, and neutrons. The protons is a distinctive part to the element. That differs one element from another because no two elements in its atoms have the same number of protons. They all have unique atomic numbers. We can change the number of electrons, which can create ions or give us a formal charge on that particular atom. And of course, if we change the number of neutrons, that changes the mass for that particular isotope of the element. Atoms with the same atomic number but different numbers of neutrons, isotopes. I'm sure that's all fairly straightforward. Protons and neutrons give mass to the atom. Because the electrons live in shells, as was first speculated about 100 years ago. And we think about the electrons as almost existing in layers, but very specialized layers or shells, which can be split up into subshells. And those subshells are made up of particular orbitals. We have, of course, the s orbital, which makes up an s subshell. It's like what I would describe as a bedsit apartment. What's an apartment with one room in America? Is it a studio apartment? Where the room is the entire apartment. Is that a studio apartment?
I think so, yeah.
Okay. So that's kind of like what an S subshell is. It's just a single orbital making up that entire subshell. And we're saying that with a 95% probability or greater, there's a maximum of 2 electrons somewhere within that subshell, within that orbital, without being in the nucleus, which is where all the protons and neutrons are. Of course, as we move further away from the nucleus, these subshells are made up of more and more orbitals. And the orbitals get a bit more fancy in shape. For the p subshell, it has those 3 p orbitals, and each of them looks like a propeller blade, either side of the nucleus. And then we get into the d subshell, which has 5 very different orbitals, some which occupy the xy axis, the xz, and the zy axis, and then sometimes occupying the space on the axes instead of between the axes, all that kind of jazz. That's about as far as we'll go. We'll occasionally talk about the F subshell, which introduces 2 new kinds of orbital. But most of our chemistry, because it's based on carbon and hydrogen, normally doesn't go much further than the 3rd or 4th row of the table, the 3rd or 4th shell. So the electrons have effectively arranged themselves into layers. And we find these layers with quantized layers with electrons. Then we find a sort of vacuous space where there's nothing, then an electron layer again, then nothing, and then electrons again. I'm sure that doesn't take anybody past the first 2 or 3 weeks of their 151 course. But worth mentioning, We basically use three rules for filling the shells with electrons. We've got our Aufbau principle, which tells us we fill the lowest energy subshells first. We've got Pauli exclusion principle that tells us there's a maximum of 2 electrons in any one orbital. And when they go into the orbital, they'll take up their location, spinning in opposite directions, which is why we often see the electrons in a diagram portrayed as these half-headed arrows. I can pull something up here. So using a cursor, which isn't very easy, so you might show one electron pointing up, and if it has a neighbor, a friend, you'll show the second one with that arrow drawn very badly, pointing down. And all it's trying to suggest from this, it's trying to imply that those electrons, as they move around in the orbital, they're also spinning, and they're spinning in opposite directions. That's because of the repulsion they have for each other. And we alleviate that repulsion a little bit and lower the energy by getting the electrons to spin in opposite directions. Again, nothing earth-shatteringly new there. And then we have Hund's rule, which tells us when we are faced with a subshell with multiple orbitals of equal energy, the electrons don't initially pair up. They will find their own unique orbital. And it's only once we have one electron in each orbital, then we start to see the electrons pair up. This is what we sometimes refer to as Hund's rule. Why share a bedroom with a roommate when you can get your own bedroom next door? Why share an orbital and face these repulsions from the negatively charged neighboring electron when you can get your own separate orbital next door and not have to face up to that repulsive force? So those three rules, Aufbau's principle, Pauli exclusion principle, and Hund's rule, show us how the electrons fill up from the bottom towards the top. Okay, no startling, revelations there. Remember, we can use the shape of the periodic table to work out the electron configuration for the element that we are looking at. This is, let's see, is my touch screen working? No, it is not. So again, I'm going to have to use the cursor. So the shape of the table was created by the Russian Dmitry Mendeleev. And the genius of the way he made up the table was that it was based on the chemical reactivity of the elements. And that chemical reactivity is based on where the electrons are in the shells of the atom. So as we count boxes in the periodic table, let's see, try something like this, maybe try red. For every box that we count, of course, we'd get hydrogen there on the left. And then on the right-hand side, we pigeonhole in helium on the far right. Not the greatest penmanship, but never mind. You get the idea. And for every box that we count, we're counting more electrons into that particular shell. So we have hydrogen and helium in the first row, like we have 2 electrons in the first shell of any atom as a maximum. Those 2 electrons going into the 1s subshell. So the period that we're in, the particular row, tells us normally the shell number that we're dealing with. The particular block tells us the kind of subshell that electrons are going into. As we count the boxes, we're counting electrons. And so we can use the periodic table to work out an electron configuration. So if we take something like, say, hydrogen, helium, lithium, beryllium, boron, carbon, we can trace across the table to work out the electron configuration. Start by counting hydrogen and helium. That's in the first shell. And we have to imagine for a second that helium is right next door to hydrogen. So we count 1, 2 boxes. That's in the left-hand block. That's counting electrons in the S subshell. And we've counted 2 boxes, so specifically 2 electrons going into that subshell. After helium, we go down to lithium and beryllium. That's 2 boxes on the left-hand side again, but now in the second row of the table. So after a little comma, we're now doing 2s. We have 2 boxes counted. That's 2 electrons again. Jump across the gap, we get boron, then carbon. We're still in the second row, so we're still talking about the second shell. But now we're in the right-hand block, so these electrons are now going into a p subshell. So 2p, 2. So I'm sure that isn't any great revelation to anyone, but these are the kinds of things I want to just quickly go over so that we're all on the same page as we start to move into new material. So we take something like, what can we have here? Maybe around about here would be vanadium, written badly. And that's down into the 4th row of the table. So we've got electrons down into the 4th shell. I just quickly recount it. As we count the boxes, hydrogen and helium, giving us 1s2, lithium and beryllium, giving us 2s2, boron, carbon, nitrogen, oxygen, fluorine, neon, for giving us 2p6. Down into the 3rd row, where it is it sodium next? I think it's sodium next, without looking at a table. Sodium and magnesium, I believe it is, for giving us 3s2, and across the gap with aluminum through to argon, giving us 3p6. Oh, somebody's trying to get in. And so on and so forth. Just remember that the row is normally telling us the shell number. The block is telling us the kind of subshell the electrons are going into, but it's a little bit trickier with the D subshell. We see that transition block for the first time in the 4th row of the table, but this is just the electrons going into the 3D subshell. D is always 1 behind. So whichever row of the table you're in, subtract 1 from that count, and you've got the D subshell number. Kind of thing that always catches people out when they're first learning electron configurations. So importantly, just based on the position of the element in the table, we can tell how many electrons the atom has in its outer shell just by counting the boxes in that period to reach it. We can also work out how many electrons the element needs to complete its shell for chemical bonding by counting the remaining boxes to reach the end of the row. So of course that means, like for something like nitrogen, which is roughly about there, it's the 5th element in the 2nd row, so it has 5 electrons in its outer shell. And to get to the end of the row with neon, we have to count another 1, 2, 3 elements, so it needs 3 electrons to complete its shell. Something like silicon below in the next row, roughly there. Badly drawn again, I'm afraid, sorry. It's the 4th element in the row, so it has 4 electrons, but it's 4 boxes away from the end of the row where argon is, and so it needs 4 electrons to complete its shell. So these are the kind of rudimentary things you should already be up to speed with when we talk about the periodic table. So that saves us a lot of time if this is all just easy peasy stuff, which it should be. Might be a little bit rusty. So of course we can write these electron configurations, and we can do the shorthand configuration, which focuses on just the electrons in the outer shell. Magnesium is 1s2, 2s2, 2p6, 3s2. But of course its outer shell is just the 2 electrons in that 3s subshell. And so we can assume that the first 2 shells are complete, just like neon. So this is how we abbreviate a configuration. Wherever the element is, always back up to the end of the previous row and use the chemical symbol for that noble gas, because that's the point where a previous shell was finally filled. So always use the noble gas at the end of the previous row. Let's see, you should be familiar with Lewis structures as well from 151. Now, I teach this as well in 141, drawing Lewis structures. It basically comes down to about 5 rules each of the times. 5 steps to draw a Lewis structure. First step is just counting the valence electrons. And we'll use a specific example of this, in this case hydrogen cyanide, HCN. And while I remember, let me just check that I'm recording this right now. Yep, I'm recording it. And so hydrogen is the first element in the first row, so it has 1 electron. Carbon is the 4th element in the second row, so it has 4 electrons. And nitrogen, as we said, is the 5th element in the second row, so it has 5 electrons in its shell. So that gives us a grand total of 10. So always start by counting the valence electrons if you want to draw a Lewis structure. And it should almost always be an even number, because we fill the shells and subshells with even numbers of electrons, 2, 8, etc. So let's look at this hydrogen cyanide example. Once we've counted the electrons, we choose a central atom. Now, Mr. Mackenzie, you're probably just taught to use the element with the lowest electronegativity. That certainly does work most of the time. But just bear in mind you might not have an electronegativity table that you can look at. So if you can't look at the electronegativities of the non-hydrogen atoms in the molecule, you can think about how many electrons the element needs to fill its shell. The majority of the times, the element that needs the most electrons is the one that's going to be the central atom for simpler molecules. So with our hydrogen cyanide example, hydrogen, carbon, and nitrogen, hydrogen needs just 1 electron together with the one it has to make a duet. And so we normally expect hydrogen to have just 1 chemical bond. It's what we call the combining power. The number of electrons the element needs normally implies the number of bonds. And so most commonly, the element that needs the most electrons will be the most central of the atoms in the molecule. Nitrogen needs 3, but carbon needs 4. So if we don't have access to electronegativities, it would be a good bet that carbon is the central atom. We can then start drawing the molecule by drawing the other atoms to that central atom. Of course, this is for very simple molecules. Organic chemistry normally tends to have a backbone of carbons at the center. But for this one, we use 2 electrons to make the hydrogen to carbon bond and 2 electrons to make the carbon to nitrogen bond. We started with 10. We've used 4 for those 2 bonds, so now we're down to 6 electrons. After connecting the atoms to the central atom, we can then start filling shells, starting on the outside and working our way in. Of course, hydrogen has its duet. We look at the electrons around it in its shell, sharing those electrons with the neighboring carbon. So those 2 electrons give hydrogen a configuration like helium. Its shell is full, it's happy. So we use those 6 remaining electrons as lone pairs to initially connect the nitrogen to the carbon and give it its octet. That's the name of the game after all, filling the shells, filling octets. And we run out of electrons, but we still don't have a completed octet for the carbon. It sees the 4 electrons which are being used for the 2 chemical bonds. So we're going to have to invoke our last step to get those shells filled, which is using electrons for double and triple bonds. So we reallocate a lone pair from the nitrogen to the carbon to give us a double bond, and then a second lone pair reallocate to share with the carbon to make a triple bond. Now I've got our Lewis structure finished. Now we have completed octets. Any questions about that? You might be a bit rusty, but remember, complete those octets for your covalent molecules. Most atoms need 8, with just the occasional exceptions of things like hydrogen, which only need 2. And then we sometimes have hypovalent elements like sulfur, phosphorus, and chlorine, which break that octet rule because they have access to their 3D subshell and can start packing in more electrons. As a basic rule of thumb for these hypovalent elements, actually, rather I can just type in some text here. There we go, just changed my own notes. So the only hypovalent elements that we'll ever deal with, and even then rarely, are things like phosphorus, which can have 8 electrons to fill its shell, but sometimes it takes up 10 for its shell, putting 2 electrons into its D subshell. Right next door to phosphorus is sulfur. Sulfur takes it a step further. Sometimes it's 8 for an octet. Sometimes it takes 2 more, putting them into its D subshell to be 10. And it could even go all the way up to 12. Lastly, the only other element that we might talk about as a hypovalent element is right next door, chlorine. Chlorine can be 8, it can be 10, it can be 12, but it can even be 14 electrons. Any questions so far? That's probably one of the biggest things you can do this week to get yourself feeling more comfortable and ready for 201. Just review your covalent chemistry and just shapes, okay? Any questions at this point? Okay. Let's see what other stuff is kind of background stuff. Valence bond theory. I'm sure you've seen valence bond theory with Bob McKenzie before in 151. We're joining the atoms together into chemical bonds, and this valence bond involves the overlap of the orbitals in that mutual space between the 2 nuclei. So really just like a handshake, the shells, the orbitals come together, and that mutual space allows each atom to share electrons with its neighbor, and it gives us a chemical bond. This is what we sometimes refer to as a sigma bond, because the electron density, there it is, that electron density in the bond is focused in the space, in the region, directly between the 2 nuclei. That maximizes the strength of the bond because those electrons feel the attraction to the protons in both nuclei. It also prevents proton-to-proton repulsion with those electrons wedged in between the two hydrogen nuclei. Remember, just like Goldilocks' porridge, that chemical bond, its length has got to be just right. The porridge can't be too hot or too cold. It's got to be the optimum length of bond when we finally get to that point where we minimize the energy of the bond. So looking at an energy diagram of a bond as we compare different bond distances, you can see we've got that optimum at the lowest energy. That's when the bond is at its strongest. If we move to the left and shorten the distance between the atoms, we can see that energy start to rise. And that's because the atoms are getting too close together. Specifically, the nuclei are getting too close to each other. And we're getting proton-to-proton repulsion. And that raises the energy of the bond. Conversely, we can also move too far apart. As the atoms move further apart, the electrons don't feel the attraction to the protons in the nucleus as strongly, and so the bond again weakens. So there's always going to be this optimum or sweet spot where we're maximizing the attraction between electrons and protons and minimizing the repulsion between protons in one nucleus and protons in another nucleus. So the exact length of the bond and strength of the bond will vary depending on the atoms we're using, because we've got that varying factor of the number of protons and that nuclear charge, the size of the atom from the number of shells, etc. So different atoms will find that different and its own special optimum bond length. Now, most of the time when we talk about bonding theory, we go beyond valence bond theory and talk about something just slightly more complicated, known as hybridization theory. You should already be familiar with that with Mr. Mackenzie, except he would have taken you through a huge number of different ideas of hybridization. For 201 and 202, we only have to know 3 versions of hybridization theory, because we're talking about just the hybrid orbitals that can be formed for a carbon atom. So that shrinks the list way down. Now, we need something more complex like hybrid theory, because valence theory does not adequately explain the shape of a simple molecule like methane. Methane with a carbon at the center and 4 hydrogen to carbon bonds. The thicker lines are representing bonds which are coming towards you out of the page, and the dashed line is trying to represent a bond which is fading into the distance because it's at the back of the carbon going down into the page or your computer screen. And so those 4 chemical bonds, naturally through VESPA theory, valence shell, electron pair, repulsion theory, they naturally spread out around that carbon shell and get as far away from each other as possible, because the negatively charged electrons in one bond are repelled by the negatively charged electrons in any other bond or a lone pair. So they're minimizing repulsion by maximizing distance and maximizing bond angle. So in methane, we see a bond angle from one bond to the next every time of about 109.4 degrees. That's as far away from each other that each chemical bond can physically get while remaining in the outer shell of the carbon. However, if we use valence theory, we'd be using s orbitals and p orbitals. And these are orbitals which have different shapes. And so how could we get the symmetry of a molecule of methane using different orbitals and different shapes for those orbitals? It just doesn't make sense. So we have to treat these orbitals, as Einstein did, as waves. And we can think of these orbitals as waves and think about how these waves come together either constructively in phase or destructively out of phase. So this background you can read, of course, in your own time, just kind of passing through it quickly. You've already looked at this stuff in the past. So it's Pauling who I explained this idea of these hybrid orbitals by treating them as wave functions and imagining mathematically how they would come together. So for a molecule like methane with a tetrahedral structure and 4 carbon to hydrogen bonds, we need all of the atomic orbitals in that second shell of the carbon. Of course, that's an s orbital and 3 p orbitals making up that first p subshell. So if we imagine them coming together constructively as wave functions, we produce these 4 new hybrid orbitals. Now the pluses and minuses here are trying to represent whether the waves are coming in together in phase, if it's a positive to positive, or out of phase, if it's a positive to negative. When they come in together in phase constructively, we make a resultant wave which is bigger than the 2 individual waves. And so as they come together, that's why one side of the hybrid orbital around the nucleus, one side that has this super big lobe, this big orbital. And on the other side of the orbitals, as they come together, we've got this out of phase section on the atomic orbital. It's coming in together destructively with the s atomic orbital. And so on the other side of the nucleus, we've got this shrunken lobe, so to speak, of the hybrid orbital. So it's kind of like the p atomic orbital, except it's exaggerated to one side. It's like you grab the balloon and try to squish the sausage-shaped balloon on one side to push the majority of the air onto the other side. So the majority of the electron density in these hybrid orbitals is on one side of the nucleus. And because we use 4 atomic orbitals in this hybridization, 1 s and 3 of the p, we produce 4 hybrid orbitals. And they're all identical in shape, which is why we get this great symmetry in a molecule like methane, because those 4 carbon to hydrogen bonds are made up of 4 identical orbitals. These 4 hybrid orbitals, each of which are known as sp3 hybrid orbitals, because that's the combination of atomic orbitals that were used to make these hybrid orbitals. Now that is something you should already be familiar with. Probably didn't spend a lot of time on it, but this is the hybridization, or one of the 3 hybridizations that we normally see in carbon. Any questions at this point? We're doing okay? So shy, so polite. You can say something. You can ask me anything. You can say, "Stop, foreigner," and shout at me. That's okay. Mr. Mackenzie does. Okay, so nothing new here. This is all kind of yawn, old stuff. It should be, but we might be a little bit rusty. Okay, so that's sp3 hybridization. We take the s and the 3 p orbitals and bring them together to produce these 4 sp3 hybrid orbitals. Each one of those hybrid orbitals is known as an sp3 because that's the combination of atomic orbitals we use to make them. This is why we get this highly symmetrical nature in the bonding electrons around the carbon atom normally. Okay. Now normally we can work out the level of hybridization for the carbon by counting the number of sigma bonds and lone pairs. Carbon has 4 sigma bonds. Each bond has the electrons directly between the nuclei of the 2 atoms. So with 1, 2, 3, 4 sigma bonds, it needs 4 atomic orbitals, and is therefore sp3 hybridization. Carbon can sometimes go through a second form of hybridization, what we sometimes refer to as sp2 hybridization, because we use the s atomic orbital and just 2 of the p atomic orbitals. They come together as wave functions, and we produce these 3 hybrid orbitals because we used 3 atomic orbitals, the s and 2 of the p. So we have 3 hybrid orbitals, each of which is known as an sp2 hybrid orbital. And again, they want to get as far away from each other as possible because we're going to fill them with pairs of electrons. Those negatively charged electrons repel other negatively charged pairs of electrons. So the simplest dynamic for 3 hybrid orbitals is in this trigonal planar shape, with a bond angle now between each of the hybrid orbitals of 120 degrees. Of course, there was one orbital that remained unhybridized, one orbital that's still atomic, and so we fit that in above and below the plane of the trigonal planar 3 hybrid sp2 orbitals. So that unhybridized orbital, that remaining atomic orbital, is normally used by carbon for a pi bond. A pi bond is when the electrons are overlapping in orbitals above and below that nucleus plane. They've got to work around the plane of the 2 carbon atoms because we already have a sigma bond there. So these perpendicular atomic orbitals overlapping give us that second bond and give us now a carbon-to-carbon double bond together with the original sigma bond. 2 pairs of electrons can't occupy the same space at the same time. So they're having to reach around the original bond that's there. So this is why we use these atomic orbitals. Now, as you can see, the atomic orbitals are perpendicular, so the overlap isn't as good. Not as good as it would be with a sigma bond, where the orbitals are flat on top of each other. So because it's limited overlap, these atomic orbitals have got to get closer together. And so the carbon atoms have got to get closer together. So a carbon-to-carbon bond, when it's a double bond, is actually shorter than a carbon-to-carbon single bond. We can usually recognize a carbon atom, which is sp2 hybridized, because it has 3 sigma bonds and 1 pi bond. The first bond between the 2 atoms is always a sigma bond because the electrons are occupying that space directly between the atoms, between the nuclei. And a second or third bond are using atomic orbitals, and we refer to them as pi bonds. The third and last kind of hybridization for carbon is sp hybridization. And as the name suggests, we're now just taking the s atomic orbital and 1 of the p atomic orbitals to produce 2 of these hybrid orbitals. Each one is known as an sp hybrid orbitals. Dealing with the hybrid orbitals first around the nucleus, again, those hybrid orbitals want to get as far away from each other as possible, so they take up positions on opposite sides of the carbon nucleus. And so a molecule, or a carbon, which is sp hybridized, will be linear at that point in the molecule. We're left with 2 atomic orbitals which are unhybridized. The first one, as before, occupies that space above and below the plane of the sigma bonds. The second one, getting away from the hybrid orbitals, but also getting away from the other atomic orbital. That second atomic orbital rotates 90 degrees and occupies a space on the left and to the right of the carbon atom. So sp hybridization, for each carbon we have 2 sigma bonds either side of the carbon, and then 2 bonds which are pi bonds. First one with the first pair of atomic orbitals above and below the plane. Let me use a pen again for that. So electron overlap there and there, and then from side to side, a third and final bond. Just being pedantic, trying to get a different color. So overlap of the orbitals there, and overlap of the orbitals there on that side. Again, because of the perpendicular positioning of the atomic orbitals, the overlap is pretty poor, and so it forces the carbons to get closer together, closer even than they were in a carbon-to-carbon double bond. And so a carbon-to-carbon triple bond is even shorter than a double bond. It must get closer to get better overlap of the orbitals. And that's it. That's all the hybridization theory that we need to know. So none of this sp3d or sp3d2, etc. We're not going to go there because the carbon doesn't have any d orbitals or subshells that it can use. So it makes one aspect a little bit simpler. So the summarization, if it's just single bonds, sigma bonds around that carbon atom, then it's sp3 hybridized, just like methane, ethane, butane. And around any one carbon, it's a tetrahedral stance for those 4 hybrid bonds. You take one of the atomic orbitals and leave it unhybridized, so sp2, we have 3 sigma bonds around the carbon and then 1 pi bond, acting as a double bond aspect for that carbon. Standard shape around the carbon is therefore trigonoplanar, based on the stance and positioning of the 3 hybrid orbitals. And then sp, we have just 2 atomic orbitals hybridized. They get to opposite sides of the carbon. And so based on the positioning of the hybrid orbitals, the molecule will be linear at that point. Easiest to recognize because we've got 2 sigma bonds, 2 single bonds, and 2 double bonds or a triple bond. Remember, after that first bond between the 2 atoms, a second or third bond is what we call a pi bond. Okay. Any questions about that? That should all hopefully just be some revision, albeit we might be a little bit on the rusty side. Okay. Did I put anybody to sleep? Is anybody there?
Yes, I'm here.
Okay. I just get lonely when there's such a epic silence.
It's deafening.
Okay. But that's hardly new. Oh, someone's trying to get in. See, oh, I click on the link to let somebody in and then it hides it again. Or did it let that person in? Oh, there they are. Right. So that looks like that was Gabrielle coming in. Okay.
Sorry, I completely missed the Sorry.
Email? No, don't worry, Gabriel. I could have. I think I put the email out maybe yesterday afternoon or something, late afternoon. I probably could have put that email out 24 hours earlier. I was just kind of stressed on Monday trying to work out what I was going to do when I found out I'd been quarantined. So we are recording this, so bear with us. We've just been talking about covalency, Lewis structures, hybridization, and recording this. I'll put it up on Desire to Learn later on this evening, so you can catch up on the things you've missed in the first hour. It should be just real pure revision, even taking it down to talking about protons, neutrons, and electrons. So I was worried that there'd be someone in the classroom kind of thinking, where is everybody? So I hope that didn't give you a fright, but you're here now. Let's see. So just in case, as a recap, we're just about to take a break, so you're just in time for a break. We'll stop for 10 minutes, let people go to the bathroom or get a drink. We'll come back, do another hour, or at most another hour. And I think that takes us through probably just about everything that I really need to talk about in chapter 1. And then tomorrow, excuse me, we come back tomorrow at 2 o'clock for a Zoom meeting again. That will be talking about chapter 2. And we'll continue talking about chapter 2 next week as well, because we start to get into some new concepts. Although you've probably talked about resonance a little bit with Bob McKenzie last year, but you maybe didn't do much of it. So we're going to do a lot more detail and examples on resonance later on. I'm hoping tomorrow is going to be the last lecture I have to do on Zoom, because my writing on a computer screen on my diagrams are pretty rubbish. But I should know tomorrow whether I'm going to be released from quarantine if I get my third negative test.
Hey, are we really going until like 5:50 today, or?
No, I think that would drive people crazy. So we will finish, as I say, we'll take a break just now, let people stretch their legs, and we'll go to about 4. I might be really mean and keep people to maybe 4:10 or something, but it would just drive people crazy, sitting at a computer screen and listening to me for 4 hours. That's not healthy for anybody.
All right.
So
Cool.
we'll be done by about 4 o'clock, okay? I promise.
All right.
Right,
Thanks.
let's take a, yay, everybody start smiling now. So take a break. We'll come back in about